All right. Thanks, Ben, for the introduction, and thanks for the invitation to here. So I'm going to present the joint work over the past few years on this topic using Fukaya category to study categorification of quantum group and not invariant. So just to don't forget my collaborators, this is based on proposal of Mina Aganagic and collaboration with Vivek Shinde, Ivan Danilenko, Elise Lepage, and Yishan Li. So we have one paper out about some fundamentals, and then more are coming about the structures and properties for this theory. So here I listed three topics. They are seemingly unrelated, but the beautiful part of the theory is that it's like the meeting hub where all the three parts overlaps. So depending on your interest, you may just choose one to focus on, but this theory has all. Okay, so let me get started by first giving you an outline for what the theory promises you. Some of them is realized, some of them is working in development. So, like, what's the output product or result? So let's fix the algebra of ADE type and quiver Q. And this is the thinking quiver. So I'm going to fix the orientation of the arrows. The choice of orientation does not matter in the end. So this is a quiver. I'm going to use the notation for representation of the quiver. So I'm going to use these numbers for the dimension of the vector space sitting over these nodes. And these square nodes are called the framing nodes, which I'm using n for those things. So K are dimension vectors, and is a framing. Okay, so to this assignment of numbers, I'm going to associate something just algebraic. So I'm going to say for each node, I and Q is 0, which are also sometimes called capital I. I have alpha I being the simple root, and Wi being the fundamental weight. So given these dimension vectors, I could cook up a total sum of these weights. Alpha is Ki, alpha I from 1 to R being the number of roots. And I'm also going to use the W as sum of NIW. Okay. So this will give me a certain highest weight and certain tensor product of representations and later. Okay, so far you can just say there are some quiver and there are some framing over the quivers, and there are some dimension vectors associated to the nodes. And maybe to be very precise, I only allow framing node on the minuscule corresponding to the minuscule fundamental weights. may not. Points. So for type A quiver, there's no restriction. For type DE, there are restrictions. For now, for this talk, I will not do the type DE. I'll just give you example in the A quiver.
Is that an essential condition?
It can, how to say, if you're willing to deal with like spaces with singularities, you are free to use non-minuscule weights.
Right, but I mean, so the theory you're
the theory for now, it describes only works for minuscule weights. So
okay, I see.
Right. We don't know how to do Fukaya category on singular spaces, or the superpotential may have some unwanted behavior there.
Right. Okay.
All right. So that's the input from the algebra side. Now I'm going to decorate. I'm going to give you a surface, and you can decorate the surface with this data. So that's input number one. Input number two, S is a smooth surface. Smooth surface with boundary. I want my boundary to be non-empty. This is also, I believe, is for making my life easier to just like when it's easy to compute, say, Fukaya category for smooth affine space rather than just a really compact simplex manifold. So I have a boundary, and we want to have like two kind of decoration or mark points. One is the interior mark points. Say P inside is also labeled by say fundamental weights. So that there are Ni points labeled by Wi. To say things as plainly, if you have like N1 points of W1 weights, just choose where to place those points, those sort of a defect on your surface. So we call these are called defect if you're like physics spiel or punctures. To be precise, punctures is like a misnomer because we're not actually puncturing the surface, but historically we just call them punctures. All right, so that's interior mark point. And then there are boundary closed intervals. So these, we call them stops. The reason we call them stops is that we imagine there are certain flow on the boundary circles, and the flow gets stopped by these marked intervals. So let me draw a picture.
Is there a difference between boundary closed intervals and just points on boundary?
No, it's yeah, there's
no can't have boundary. Can't have.
No, there's no corner. Yeah.
Yeah.
Right. Yeah. Somehow it's easier to think like you can glue two surfaces with stops where the stops glue the two stops. If you're at a point, it's kind of hard to imagine you're gluing two things at a point.
Oh, so is it like you have points at the boundary, but there's at least two of them?
Yeah, the point is that a stop sort of is a Legendre, but you can always think the Legendre comes with a ribbon, which is like a little bit of one technique.
Ah, okay, I see.
That's right.
And like that choice of neighborhood is not canonical, but you can always make two of them agree by picking a smaller one.
Right, okay.
That's useful when you do Blu-ray.
Okay,
So that's
Exactly. Yeah. So I'm drawing a picture of two surfaces that wants to glue along the two stops.
I see. So the closed interval I should think of as really like a point.
Yeah.
Okay, I see.
Well, it's a neighborhood.
Right. So let me just give some example for what kind of surface we can consider. For emphasis, I'm just going to highlight the interval like this. And here are some mark point. And I don't know, can just label them W1, W3, W1. And we can also have things like this, a cylinder, and can label things this, W1, W2. Okay. So these are like the input where we specify something about the quiver and something about the surface. And what's the output? I'll give you something like a black box first, but then I'll later explain how to build this black box. Output is something called a Fuchsin of this category. Fuchsin G, where I have this S. S including the stop and the defect data. All right. And the subscript, I'm going to put this alpha. Alpha, remember, is about the number I put in the circle. So output is a category. Okay. Well, that basically I like saying nothing. Like like a input is something, like output is a set, and everybody can produce a set or a category. What property does this have? So first, it has some nice dependence on the positions of the punctures and position of the stops. So isotopy of defects and stops induces equivalencies of categories. It's like locally invariant, but it has interesting monodromy. Also, one can merge and split defect. Defects, depending on how to say. So, for example, if you have two fundamental weights and you consider the corresponding fundamental representation and consider their tensor product, it will decompose into a direct sum of other simple representations. So it may not be like lambda, so I have multiplicity. And we can consider the inclusion or projection of a direct summand. Suppose Utah is a certain VWK inside VWI and say VWJ, and pi is the corresponding projection. Then
Is there some multiplicity one thing going on?
yeah, that's a very good catch. So far, the only examples we have done are multiplicity ones.
Okay.
Yeah. This part is like still work in progress, so the details are not yet figured out yet.
Okay.
We can upgrade these linear maps. To functors. So let's see. Let's call these guys right. So if you have a Fuchsin of a puncture labeled by WK. So this dashed line means like it's a local picture inside a surface. Fuchsin.
So isn't that the surface should be infinite or it could be finite space?
The surface?
Yeah.
The first surface is a compact surface. It's like a surface, closed surface with boundary. Oh, sorry, it's a closed surface. Yeah. So, okay, maybe I should say that for any surface with this local picture, I can do this local multiplication. So maybe this. Okay, I'll just say that. This you can imagine.
Is the assertion of a left-hand side as written is not defined, but this I should think of it as part of a larger surface.
It's part of a larger surface.
But is there a way to define something that would be denoted literally as you wrote?
That's a good question. You can write the most naive thing, just put this thing on a small
Right.
disk.
Yeah.
But that's doesn't capture this compatibility with being able to insert into bigger space.
Right.
So I don't have a good language for saying what's the bigger property.
I see.
Right. So I better just say universal is a local multiplication. And this functor preserves weight. Let me explain what do I mean by weight. Preserves the weight. It means my domain category has a total weight being this W minus alpha. Okay, so this is the weight of assigned to a surface or assigned to a quiver. When I do this multiplication, I'm essentially changing this part, this highest weight part. I'm also need to change correspondingly what is the how to say the root part, because this kind of morphisms preserve the weight. So for example, I can start from an empty space. and produce something like this. So what this tells me is that I can consider this V0 embed into V1, tensor V1 in say SL2 red. And in particular, I'm looking at the zero weight space. And indeed, 0 equals to W1 plus W1 minus alpha 1. And similarly, you can reverse the picture. All right. So to summarize, what we can do is that you can categorify certain weight spaces of tensor product representation, and you can categorify linear maps between representations into functors between those categories. I mentioned something without explaining what do I mean by categorifying tensor product of representation. So let me give you some example. But before I say what I want to say, namely, I'm going to take the growth-ended group of these categories, and so these vector spaces have some actions. I need to tell you what do I mean by actions.
Can you say, so I can parse that this Fukaya or S subscript alpha, what's the sort of subscript alpha to it, like, what's it doing? Is it sort of telling me that I'm taking some subcategory of Fukaya category?
This sub alpha is trying to tell you the so there are a sequence of spaces, but one for each different alpha. They categorify different weight spaces.
I think that like there's something called like SimG of that. There's something called like the symmetric product of a surface.
That's right.
And I can take its Fukaya.
That's right. Yeah. So maybe let me just say that what does a subscript mean in the simplistic case? It corresponds to the symmetric power in some sense. So like SimG, say S, let's say of K1, Kn. It's roughly speaking certain category of product of I from 1 to R. Okay. This dot dot means it's not literally this space. There's some space that has a vibration over this space. I'm
Right,
taking
now what is the G? I assume the G was about the symmetric power. The first section. What's that do then?
this G tells you what's the thinking quiver.
That G is a math problem.
Oh, I see. Okay, so that I see.
No, it's not genus of anything. It's Lie algebra. It's
Yeah, the algebra G.
Lie algebra.
Okay.
Oh.
I sort of so this was the wrong space.
It's related to category of round space, but you can say I'm not. There's some fiber over this space. It's not literally the round space. So that's what I was mentioning in the second part of topic of the talk is a factorizable space, something fibered over the. I'm not sure whether I should call that a run space, or because so far I'm just using the disjoint union property. Yeah, right.
This I would call some label configurations.
Yeah. The base is labeled configurations and I colored.
Yeah.
Yeah. Right. Yeah, exactly. That is the space. This is that Stava space favored over the factorized over the place. Okay. And another property is the gluing property. So if I have a surface, if S admit an interval cut, which is of the following sort. Suppose here's S. And the interval cut is a embedded interval that allows some color neighborhood so that S can be decomposed into SL, SR with intersection. SL intersect SR is H times like this. Then we have a map. Then we can have a map like focusing alpha L. Okay, I need to say specifically what does SL look like. For this SR, this cut becomes a stop. The cut becomes stop. So we have a merging map. We have a,
Sorry, just so that I understand the picture, should I interpret the picture as being in the plane, or is that some kind of a handlebar? Like, is that an interval or a
it
sort
is
of
it
stage thing?
it is an interval. It is a disk.
Ah,
Yeah. And this cut is like interval cut.
okay, I see.
It's like interval.
Okay,
Yeah.
great.
But that's a good question. There also are related concept of the circle cut, where you indeed have some like cylinder and you cut in the middle of the cylinder, and that is much harder. Okay, so we have some functor like this. So this kind of a merging functor, merge functor. And their adjoint are called the split functor. We have both the left adjoint and the right adjoint. In some cases, they're related. In some cases, they're not. In the case where if all the surfaces has at least one stop on the boundary, the surface, the categories are especially nice. It has some Helm finiteness property. Then the left and right adjoint are very, very easily related. So yeah. But for now, let's just say they have this merge functors. And split adjoints. Merge. All right. So we have these kind of properties for these categories. And what we can do with this, so first let me show you where does quantum group come from and where does the representation of quantum group come from. I will first introduce the direct sum over all the weight spaces. This is Fuchs G as this direct sum of all the alpha summing over the positive root lattice. And I would just, for shorthand notation, I'll just denote this by Fs. So first thing we can notice is that this guy, which is a disk with two stop, is a monoidal category. It follows from because interval glued with interval at end becomes just another interval longer. Denoted as A. This is the same as the Rouquier's pretty U or U minus category, if you read Rouquier's paper. And the Fukaya category
Is it U or U minus? Is it categorifying N?
U minus.
What?
U minus is the categorifying
Or
UG N minus.
Yeah.
Yeah. If I have a disk with one stop and with some fundamentals Wi, it is a monoidal module. It is a module. Because I put the stuff on the right, it's sort of like the right A module, but in such generality, it's kind of a it can be also put on the left and view it as a left A module. I'll just be vague and say it's monoidal A module. And now we can say what they are. If you take the K group of this thing associated to a disk with two stop, that is UQ N minus, the negative half of the quantum group. And if I take this would just be the representation VWI. So let me just say what these on the K theoretical level, how does the dictionary go? So the objects in this Fuchsim of the disk, or let's say a generating object, are things labeled by are straight lines labeled by, say, F alpha I1, F alpha I2. Sorry. They are labeled by this sequence of roots. Okay. This M. So that sum of all these roots, this is the same as alpha. So splitting the total sum of simple roots as sum of simple roots. So this corresponds to the F alpha 1, alpha I1, I2, alpha IN. inside U cube and minus in terms of algebra elements.
There is not just a map that's
We'll get back to that. For now, that merge is only just a functor. It's not an equivalence in any sense. Because you can say it can generate the object, but it will miss the morphisms. It will not reproduce the Helm space, so it's not fully faithful. But on the level of the K-theory space, you may not detect that.
Is it like that some words like Jacobian? Or it's more like different?
So I don't know, what do you mean by Jacobian?
From alpha am that word like Jacobian in traditional calculus?
I'm not sure. Yeah, they're related to Jacobian in the traditional calculus. I'm just saying, you have a bunch of, say, you have 2 copies of alpha 1 and 3 copies of alpha 2. You have a totally 5 objects. You want to place the 5 lines in the disk, and 2 of them labeled by alpha 1, 3 of them labeled by alpha 2.
So it's like storage space for that exact value, how I understand.
Yeah, you can think like that. Yeah.
Can I ask, if I want to turn off in UQ and minus, if I want to turn off the Q, what does that correspond to in the Peng category?
Great. So these categories, they have a certain extra grading, or you can say that the Fukaya category, the actual space we consider has certain a certain cyclic cover, like a R to R mod Z, and the category associated to this cover has that extra grading, and those grading give you certain this Q in the Grothendieck group.
I see. So the fact you get UQ and minus is due to the fact you're actually
Exactly. That grading comes from a H lower 1 class in H upper 1 class in this curly Y. More precisely, we have a map C to C star. And this guy is just the unwrapping of that map. And this map is given by certain non-vanishing or invertible. Okay, so this is a Coulomb branch jargon, some monopole operator of this space. But for now, I don't want to focus too much on the Q part. All right. So on the object level, this is like an easy bijection. Maybe it just doesn't say anything deep. Over here, let's say how does this dictionary go? So if I have if my alpha equals to 0, I think of alpha as the amount of lowering operator applied to this highest weight state. If my alpha equal to 0, then this just corresponds to VWI weight, the highest weight. And say I apply certain alpha I1, alpha I2. This is just applying, okay. I'm sorry, I'm going to use the right action. Right action. So we apply alpha I1. was the red module of the universal enveloping. This V is the highest weight. Highest weight vector. It's not equal to this. Corresponds to this. So this object decategorifies to this state. And you may wondering, it seems we can keep on piling like lowering operator to a given highest weight state, and why this becomes a finite dimensional representation, right? So something very nice and surprising. Before I say something very nice and surprising, I want to say, indeed, that it is the right intuition. If you do not put a puncture here, but instead you put a hole here, a colorless blend, just a black hole there, or not black hole, then you indeed would get the Verma module. Anything you can write down is okay. But since it has certain defect, there is certain vanishing result. For example, if you have SL2, if you apply twice the lowering operator of alpha 1, you can show that this corresponding geometric Lagrangian is actually null homotopic. So this object is actually 0. So these results are based on existing work by other people like this Hovanov, Lauda, this the quantum group categorification people. So what we do is we build a link between our geometry into their algebra. Okay, so far I told you about the properties of these categories, what they can do, and how it decategorifies into this usual representation and usual quantum group. But you notice that here I only use very simple surfaces. I only use a disk with 2 stops and disk with 1 stop. But I can use more general geometry, for example, disk with 3 stops. And that brings us into this structure of tensor product.
Right, is there something that corresponds to the entire quantum group?
Good question. What's that? Same question, right? So these object merging, how to say? Yes, the short answer is yes, but it's not geometrical. The lowering half of the quantum group are realized by these merging functors. The Rising operator are abstractly defined as the adjoint of these functors. So you can say, indeed, we don't invent new things to say the word adjoint, and things are defined nicely.
I see. I mean, so you named a category whose objects. Sorry, is it something simple? This the one that categorifies this one, yeah. Well, anyway, you named some monoidal category that
right.
Categorifies it, and I'm supposed to take adjoints to get the other things. So
yes.
I
don't have the carton.
So if I guess then the question is, if I build another category where I formally make adjoints, like I add kind of duals,
right?
All the monoid to all the
right.
Like I rigidify it. Would that give me a categorification of the full quantum group?
I'm not sure how you deal with the carton part, and yeah, I don't.
Notion verification of the field sheet not configuring this by itself. That's right. So I'm not even sure that it's found.
Yeah, so the usual people usually do this U dot version of the quantum group to put this idempotent weights, but that and they enforce this EF minus FE equals to some sum of identity. But that I think that is like too eager to quantize the thing. For example, if you try to compute Fermat module, it doesn't satisfy that condition. EF minus FE equals something. So here, doing half, I think, is like the most natural starting point. I'm not sure whether there perhaps there exists a natural categorification for the whole quantum group, but I don't see it right now.
Or if I do modules, do you only get the fundamental ones or?
So far, I only categorified the tensor product of a minuscule.
Oh.
And you can build other weights by projection operator or as a subcategory of this tensor product. Yeah.
Is it possible to relate it to other applications?
Yeah. There are many nice relations. I'll talk about that right now. If you mean by other categorization, you mean some says Tropos category O stuff or this arc algebra?
Like this pure sheets and subspace related about how much money. Just where I mean, but also naturally, they're also naturally given communication of
Yeah.
not products of still.
Exactly. There's a 2D mirror symmetry relating the coherent shift part and this high realization.
It's like equivalent pattern.
What's that?
So it is an equivalent pattern.
Yeah, it will be. Yeah. Great. All right. Right. I was going to I draw the circle. Now I'm going to talk about so the disk with the 3 stops. So if I give you the disk with the 3 stop, what I can do is that I can use it to describe certain merging operation. So you want to say that the category of this guy okay, the disk with 1 stop but 2 punctures is built up by gluing elementary objects. Okay, so far I'll put a question mark here because this is a wrong statement here. These are well defined. This is like a fundamental here, W1, fundamental, category 5, fundamental W2. This is whatever categorifies this guy. But what the heck is this tensor product? If you think in terms of just the naive tensor product of categories, that's not going to give you the right answer. But if you think like at one moment, how things should categorify, you really would discover that this tensor product should be monoidal tensor product over the algebra, monoidal algebra object. And then it is indeed correct. Okay, so one thing that is a key power engine for the whole story is to define and compute this tensor product, categorical monoidal tensor product, and relate it to geometry. Like with Vivek, we're working on proving that this monoidal tensor product corresponds to actual gluing of the surface. So let me say a word about that. Okay. So this is about maybe the second topic, that is category of reservoir spaces. Okay, so what is a factor reservoir spaces? Definition. So maybe factor reservoir spaces, or should say factor reservoir vibration. Space. S is the following data. So S is a so make my life easier, I will assign associated complex factors. It's a complex curve, smooth complex curve, analytic. So I could be thinking about certain open disk. And CMS is this disjoint union of the symmetric product. And this X is also the disjoint union of all the symmetric product. And this pi is corresponding to sending components here to components. I mean, you're welcome to think that S is a smooth affine, and X is also Xn is also a smooth affine, and these maps are that. Some nice condition about these maps. And such that if you have a disjoint union of open subset in U in S, the usual factorization property holds. So for U disjoint V inside S, we have pi inverse of nice. Okay. Technically speaking, these are very limited. There means a colored generalization where this n is where this n can be generalized to this sum over, where n can be generalized to this. I called that k before, but n1 to nr, and there's a colored symmetric product. So far this written is only for SL2, the algebra. So there's a version of a gluing theorem. Gluing theorem. We can call that exponential of GPS gluing. If you know what's GPS gluing. Okay. So what is gluing? What is descent? What is a sheath? You're saying why do you use this instead of a run space? Well, for one thing, this thing naturally comes up for the examples we consider, so we axiomatized that way. I don't exactly know the difference between symmetric space and rank space.
Well, it's not going to be determined, but it's going to space.
Mhm.
Why are we using this instead of the rock space?
Maybe eventually the correct way formulation is a rank space.
This is the. Looks very much like categorifying the stepwise sheaves description.
Exactly. Exactly.
That's what's there.
Yeah.
BFS. Business.
Okay, I'm now familiar with the PFS reference.
There's one other thing we're checking. Factorizable. Quantum groups and things that's sheets.
Okay, yeah. Yeah, I know.
So for this looks really similar, but I think you're going to be using different factors in space as well. So they use well, some version of that. I mean, in their thing, this thing comes up as some positive part of the F inverse Bunyan for the torus.
Torus? Yeah.
Yeah.
So for
like you put positive roots and then
Mhm.
these are you.
So for example,
those as label like that.
For example, if S was like this or C, then this xn is just this open Zastava space where you map like C to P1 hitting infinity n times. So it's a space of polynomials QZ, 3Q. Then so it's kind of this space.
Right.
Yeah.
What is supposed to be a mirror to that?
Mirror to this.
Yeah. That's the wrong.
Right. Maybe we leave the mirror to the third part. Yeah. This space is supposed to be the A size space. I'm going to do Fukaya category on this time. Yeah, so since I'm here, I'm just saying degree Q equals to N and PQ coprime. And the map from Xn to SimN is just sending PQ to Q, where Q give you the N roots. Okay. So I was going to give some philosophical musing on what is a sheaf. So we all learn a sheaf like this. Do you have some open set U, open set V, and open set U intersect V? What the sheaf supposed to do is like sheaf supposed to tell you that sorry, I'm using the same notation F as the sheaf. It's supposed to tell you that if you build this commutative diagram of restriction maps, this top guy is determined as the limit of the bottom part of the diagram. In other words, for example, a section on U union V is a section on U and a section on V so that they agree on overlap. That's the usual shape. And this shift notion has been generalized, property has been proven by Ganatra, Pardon, Shende for Fukaya category for Weinstein manifold, or in general, some real-world manifold with enough Weinstein structure. Well, they basically, I'm just going to give some example. What they prove is that suppose I have a disk, say with some holes or something. and I can cut my surface into this shape. What they can show is that this Fukaya category of SL, or more precisely, wrap Fukaya category of SL, and wrap Fukaya category of SR. Well, for now, let's do the colimit version. Yeah, well, let me just do the limit version. So you can put a module over this category if you wish. So the category of SL union SL. All right. You can think that this indeed is sort of like a shift property because the category of this sort can be computed as certain shift over the red guy, which is called the skeleton of the space. And this red guy lambda can be written as lambda L union lambda R along with this middle segment. So one can also say this is microlocal shift lambda L, microlocal shift lambda R, restrict Okay, so far, this is just an old story saying that you can compute the old, say, sheaf on the base space, or this more generalized macro-local sheaf on the skeleton, or its category of the thickening using like a local to global property. Things agree on the middle. But now, suppose you want to consider something like, consider like 2 points, like for category of symmetric product of this surface. This is not the right picture to consider. This is not enough because if I have a 2 point, this would be simple. If I have 2 points that can freely roam on the surface, many situations can happen. 2 points on the left, 2 points on the right, one on the left, one on the right. And these are not clear-cut situations because what if 1 point is in the middle? When in the middle, it can be either belong to like both points on the left or it's the one left, one right. There are ambiguities. There are more ambiguities. But if you organize those ambiguities, you see they form a pattern. And that pattern exactly matches the bar complex of this tensor product over this whatever monoidal thing in the middle. So let me just write down this pattern first. So I'm still using this picture. I'm just going to consider the category of symmetric product of this S. I'm going to write down certain numbers without explanation, and then you are free to invent your own explanation for these numbers. Okay. So far I wrote down these 3 layers, and there are several ways to interpret these patterns. One way is to is to say that we have 2 points. Let me just schematically say this is SL, this is SR. So 2 points roaming on the entire surface S. And if I want to split this into two parts, we have a 2 on the left, 0 on the right, or 1, 1 each, or 0, 2. And here, this 1, 1, 0 corresponds to the situations that 1 point on the left, 1 point in the middle, and nothing on the right. And similar is 0, 2, 0 and 0, 1, 1, 0. And the final intersection is where there is no point on the left, no point on the right, and 2 points in the middle. And 2 points in the middle has a gap between them. So if we model this symmetric product over the surface in the middle part, we're actually just considering symmetric product of 2 points moving on the real line. So this is x1, say, let's put that x2. And we're looking at this region above the diagonal region. So how can we cover this space using these open sets? So here is a way to consider such covering. The bottom line is that I'm going to cover this guy by 3 open sets labeled by these 3 guys. And the rest of them automatically come from intersections. So they form a check complex of open set. Okay, so let's say, suppose this endpoint is -1, this is +1. So if 2 points are both on the left, I'm going to write U20 as x1 less than x2, and those points are less than 1. And U02 is where those points are on the right. You notice that they have overlaps because I'm taking a very generous notion of what is on the left. It's included in here, a generous notion for what is on the right. It's enclosing in this interval, in this half one. And this U11, well, this is going to be 1 point on the left, x1 less equal than 1, and 1 point on the right, x2 bigger than -1. But I want to impose certain gap. I want to impose certain gap. x1 is less than x2. I'm putting an epsilon here. It's a new notation. It means that x1 is less than epsilon, x1 is less than x2, and the difference is bigger than epsilon. It's a gap to separation.
So your U is supposed to be closed sets.
It's going to be, oh, I'm sorry. Thanks for pointing this out. So on the diagonal, because the diagonal part doesn't matter because that's the actual boundary of the diagonal. I want them to be open set. All right. Okay, so let's draw the pictures and see how the intersection comes up nicely. So you have x1 less than x2 less than 1. So x2 less than 1. So that's like given by this picture. This is a U20. And This is U02. Okay, 2 points on the right. And finally, we have this U11. So first of all, it do not touch the diagonal. So it's something like this. And then they chop off at 1 and -1. X1 has to be less than 1. So it's like maybe here. Sorry, this picture is maybe not very clear. Let me just try to draw it again. So one things like this, one things like this, and another things like this.
Can you just say again, sort of schematically, what are these supposed to represent? Like the 2,0 is one where they're both on the right-hand side.
2,0 are 2 points on the left, 0 on the right. And this is 0 on the left, 2 on the right. And the 1, 1 is 1 on the left, 1 on the right.
Well, what about the numbers? What about
the next row? Yeah, these are going to be intersections of these two guys.
I mean, do they still have some interpretation?
Yeah, that's right. It's like 1 point in the middle. 1 point in the middle so that it can be both interpreted as 2 points on the left or 1 point on the left, 1 point on the right. These are like 2 points in the middle that can be merged.
The suggestion is you're supposed to think of these as terms in the bar complex, and there's 2 copies of the algebra at the bottom.
Right. So you're supposed to, yeah, the punchline, as Nick said, you have a graded algebra and a graded module. The grading are indexed by the number of points in that module or algebra. So here, I'm supposed to tell you what is tensor A with grading 2. And on the most naive level, tensor over vector space, I can put a 2, 0. I can put 1, 1. I can put 0, 2. On the next level, in the bar complex, in the reduced bar complex, which I don't allow 0 in the middle, I have a 1, 1, 0. I have the other things. A2, I'm 0. And so on. And the next is I'm AA. So this diagram indexes both the diagram of the bar complex and also a diagram of the check covering GPS. We're putting as a GPS sectorial check covering for the space. So these so far are living over sim2R. You can pull back to live over sim2C. And this claims that they form a GPS cover once you correctly define what's the symplectic structure near the diagonal, the smoothing of the boundary near the diagonal, things works out. And GPS machinery guarantees you that the colimit of this guy the colimit over this diagram for this Fukaya category reproduces the top guy. And you can reinterpret that as the derived tensor product of monoidal category of M and N over A to give you the top guy. All right. Yeah, so I'm a person of explaining using examples, but the example may be too confusing to get the point. So the result is that geometric gluing can be realized by algebraic gluing. So the Fuchs theme of SL union SR is Okay. So that's the theorem.
Do you actually exhibit a neutral sectorial power of the symmetric power?
Yeah, that's the main part. And also not just of the base, you need to lift that to the factorization space.
How is this related to Dewey, who is like 2010 ICM address? It's all about Fukaya categories of symmetric powers. Like people have thought about Fukaya categories of symmetric powers before. Right?
Exactly. So those are, like I should mention, the Higa-Floor people who does category in the global way. And then there's also Douglas and let's see, thank you. And who did a different version of a co-product, which is my formalism is very much inspired by their formalism, but it's in a different way. Because they uses, in my understanding, is like infinitesimal rep category, not rep category itself. So here we're dealing with like the algebra, how the algebra glues, where they are more dealing with how the module glues. And also there are previous works by Dickerhoff and Tobias Dickerhoff and Yankee Lakili, yes, on the same. This is also pretty much inspired by their work. Well, for the case where there's no fiber, just symmetric put up the Riemann surface itself. Yeah, so there are a lot of the previous works where this is inspired by.
But nobody has sort of given this general sectorial.
That's right. I believe the formalism of showing this thing as tensor product as a bar resolution was new. Because this thing looks very degenerate. How to say? You would want to truncate and simplify your diagram beforehand, but that won't give you some easy or canonical result. If you try to do this direct computation, try to derive formulas, that'll be hard. But turns out abstract things is like, although not as useful as concrete formula, but they give you some correct forms. Right. So maybe another thing to say that we believe this thing could be general thing, and this is like advertisement for people working on Fukaya category, maybe exponential Fukaya category of symmetric product with this kind of a monoidal gluing property is interesting to consider. And here we're considering some sort of like a partial of the story because our things are like fibered over 2D. We're basically using the base two-dimensional space is gluing to control the whole thing. But one can consider some more genuine higher dimensional symmetric product. People like Honda, Honda and his collaborator consider this higher dimensional Higa-Floor theory, which basically says I give you, say, a twin-dimensional Weinstein manifold, consider it's a symmetric product, and do category on it. So they define a certain formalism for defining things. And it's interesting to see how what algebra object or structure would this gives you, and how to get this kind of a gluing theorem.
Is there a way to deal with the fact that these are no longer smooth?
They didn't do symmetric product of the space itself.
Ah,
Yeah.
so I mean, that's the thing about surfaces, is that symmetric powers are smooth. For higher dimensions, that's not.
Yeah. Yeah. That's right. That's right. So in our case, so this is like the Higa-Floor version where it's just the surface. In our version, it's not we define. The thing naturally comes up, this factorization space is some sort of a horizontal Hilbert scheme, which is like smooth. And it has a nice map to the base. And that's what gives us all the properties we want.
Is there a version of your story that compares to Hilbert's law? So I mean, I guess morally this should be like GL101.
Yeah, this is GL101. Yeah, sorry, I should say that it's analog of Fuchsin, say G, or not Fuchsin G, book of X. I don't have a good notation. It's called Fuxim. It's what we use in the paper. Fuxim X, suppose X is the factorization space. You replace all the S by X, it still works. Okay, so this with feedback. It's a work in progress.
This X, yeah.
X is the factor. Okay, I should be more careful. Is the factorizable space over the base S. And example would be the, say, horizontal Hilbert scheme over S. So example. So you start by having some initial initial space for one point, one particle mapping to S1, and then you take its horizontal Hilbert scheme construction, and this maps to sim S. And it satisfies this factorization property. I mean, we haven't done the full proof yet. The main difficulty part is construct the Liouville structure once in the structure, so it's compatible with everything. But we believe that this space also satisfies those properties. So in particular, those things that considered by like Seidel and Smith, where they consider some alien surface fiber over some base with some cone-like singular fiber, would satisfy this property as well. Say again?
There a way to go from this to the case of the pump?
That's a good question. So far, GPS does not give you that for free, but there's a new version of a gluing that is like recently being considered by people. This is like say, let's say, suppose I just have a Riemann surface, compact Riemann surface, and I want to do some pair of pants decomposition of the base Riemann surface. So the overlaps along circles now. And there are some like co-limit or limit diagram regarding that shows how the global Fukaya category can be built from the local Fukaya category. And what you want to say is like exponential version of that. And that's like two-step in the future. Right.
This glue you just mentioned assumed that you had an open advancements when the puncture cylinder.
Right. Yeah, that was like use the puncture to triangulate your stuff. That one is more, how to say, more global or canonical. But it's a good starting point. All right. What's the middle Zhou? So the quantum group for GL11 and the not polynomial associated with GL11 is about symmetric product of the Riemann surface itself. Where SL2 is about something else, the horizontal Hilbert scheme.
So this you're at the start of this talk, you said we fix this sort of thinking diagram corresponding to something else. Does this also work with GL1?
Yeah, it works with that. Yeah, it works with super, and it can work with GL/M, which is still under development. The formalism has the potential to be very general. It just needs to be developed.
But I have to say we should. There are things we should consider, right?
That's right. That's right. For GL11, it's just a surface itself. There are another version for this GL11 where it's like you don't consider surface itself, but you consider surface with say with C and C like fiber over the surface. How to say it's like an orbifold or sorry the okay, so this is maybe getting a little bit ahead of myself. Okay, how should I say? So for GL11, there's a simplified A model, and there's a more, so to say, honest A model, where you consider some potential on the fiber, and by Orlov or symplectic version of Orlov can reduce to just the lower dimensional A model. But that's for GL11. And for GLN/M with this fact, maybe you have to use a more complicated version of the A model. But still, the factorization in space and that formalism should work. In the ADE case, right? So let me give you the example for. Is SL2 okay? Right. Um, so this okay, so this is like just telling you the space without puncture, but just two stops. So this YK is U port K. Which you can write it as spec of C. Okay. It's sort of an alpha blow up of a symmetric product of this guy. And WK, let me tell you WK in some open patch of this guy where all the yi's are distinct, this WK is going to be first yi squared plus summation of okay. It consists of two parts. In this part, sum of yi squared because the base disk has like two stops, and sum of y squared give you the two stop. This part is not so important. This second part, first is that such expression extends from being just a rational function, being a holomorphic function on the open part where yi not equal to yj, extend to the whole space. And that is a holomorphic function on yk, and one can use that to define a trivial sector and define the Fukaya category.
And what does this mean? Fukaya category, but think of the super, because that's some kind of Fukaya saddle category.
Yeah, Fukaya saddle category, right?
Right, and for general IDs, the corresponding space is the one branch of the corresponding word.
Yeah, exactly. Yeah, so for general ADE,
What's the potential? In this time, just try to describe it. So describe
it consists of the say again.
saying the school branch is some preferred function.
Right. This is from your paper about Coulomb branch. There are some monopole operator associated to the co-weight of the gauge group. So let me just write strictly. So let's say we have this. So this W is summation over I from 1 through R, from J from 1 to K. Well, let me write down this things written in the abilized coordinates because that's like more intuitive than I write down the more invariant form of that. So I and I comma J and so suppose you have some other I prime map to I and you put sorry. Okay, so this is a gigantic expression. What this means, first, what are the variables we have? For each node, you have a two set of variables like y ij and xij, and i's from 1 through r, and j goes from 1 through to this dimension vector ai. Okay, so the whole Coulomb branch as a dimension is twice the sum of these numbers. So this xi and y is like the abelian. You take some abelian cover, and there's some nice coordinate on the open subset of the abelian cover. And for each node I and each like small subnode j inside that big node I, you can consider like the numerator and denominator part. So the numerator part, so depend for each incoming arrow, you put some factors of some incoming arrows base coordinate y with this current coordinate ij. You take the difference at that use as numerator, and this like the self interaction contributes to the denominator. And this can be written more formally as a Coulomb branch function. So this is R of, I forgot the precise thing. It is on the ith node, you put the first fundamental co-weight. So on the Coulomb branch, there are some functions produced by co-weight into the gauge group. And here, the gauge group is the product of this GLK1, GLK2 thing. And here you're looking at the ith part, and you harm the first loop into that guy to give you a function. And that function give you this guy. Right, and don't ask me where does this function come from, why this works. Like physicists predict this guy give you some nice answer once you integrate out the fiber. And I heard that's how they came up with the formula. But they, I mean, Mina, Agna, Najik, and maybe earlier Gayoto, Wheaton. I think this is a paper explained by you and the collaborator explaining Gayoto-Wheaton superpotential in terms of the sound. So it's that potential.
What do you do for representations?
Great. So these are like the pure thing. What do I do about representation? If I have some, like say, W1, W1. Let me do this SL2 first. I produce a function, say f. Say the location is at point A1, A2. Okay, so it's a function that vanishes at those points. I'm only just multiplying those functions to here. So I'm replacing this 1 by this f yi.
So you keep the same space for one time potential.
Exactly. Yeah. So earlier you asked what happens if you have a non-minuscule weights. For the space, nothing happens. It's still smooth. So superpotential, something bad happens. But you could ask what bad can superpotential be? It's bad in the sense that you could have singularity. The category is singular, and there are objects in the category where the harms like unbounded in the homological degree. In that sense, that if you wish, the analog is like you have some fiber that how to say. So maybe you can have like Settler-Smith space like 1 minus A1 minus A2. It's a perfectly good space when A1 is not equal to A2, but when A1 equals to A2, the space becomes singular. It's that kind of singularity. But it's not happening in the space level. It's happening at the superpotential level, where you imagine you're somehow chopping off the space and the remaining part is still smooth, but there's some superpotential controlling part. It's singular. I'm talking riddles, I'm sorry. That's that part is still under development, how to deal with the non-minuscule stuff. All right, great. Thanks for all the questions. Let me see what else I want to talk about. I covered a lot of the things.
Is it possible to make some statements about what the mirror is to these things?
Oh, great. Thank you for reminding that. I want to talk about 2D mirror symmetry. I came into this subject, want to learn some 3D mirror symmetry. It turns out there are some like interesting 3D mirror symmetry, which I still don't know how to understand. About some skill, how you do that, duality stuff, and how things are related. Let me first make the statement and then explain some examples. All right, so recall we're given this ADE quiver Q and framing and dimension vector K and W. It's kind of you just think if it's a non-minuscule way to just set that to 0. And one can produce from this a additive Coulomb branch, where the input for Coulomb branch is a gauge group. And a representation. So here, the representation has two parts. That's first the internal part and also the exterior part. And okay, and the G axon these guys. So it's negative. Okay, so the Coulomb branch that's given by this Gn, And usually this space is singular, so we want to consider its resolution. And the resolution depends on some parameter, so some beta. So the coherent shift of this guy resolved Coulomb branch. And then Webster proved that. Webster. This coherent shift category admits the Turing generator, and the endomorphism of the Turing generator has a nice name called cylindrical KLRW algebra. And it's related to a certain cylindrical KLRW module. And what we are proving, and not quite finished, we didn't quite prove the generation property, but expectation is that it's a Fukaya category of a certain space, what space. I mean, in our new terminology, it's Fuchsin of the G determined by the Dinkin Kuiper of the cylinder. And now I'm going to put some like decoration here so that the sum of this all the W all the punctures equals to the IW. And I'm looking at the lowering the simple root space alpha. Alpha is sum of Ki. Alpha. Okay. So what we actually prove is that we prove that there's a fully faithful embedding of this space and this subcategory into here, but we didn't show that the object generates.
So on the left-hand side, we have various sheets and some synthetic resolution.
Yeah.
And on the right-hand side, you're supposed to have like Fukaya category similar to
Yeah. Let me.
The space in this time.
Yeah.
Know that the space is comparison.
Right. Good. Maybe let me not use this the fancy black box packaging.
That show.
You're asking in what sense it's mirror symmetry? Like
Yes.
If we didn't have the super potential, by just ignoring the super potential, just like the polygraph category.
yes,
Would I get coherent sheets on that theoretic Coulomb branch?
exactly.
Well, that's exactly my problem, because now in one of my problems I found means build my question. So if you do the stuff with our representation, then the space itself doesn't change. The only change is super potential.
Yeah.
And you can see that the mirror too, obviously the space changes.
In mirror symmetry, you can pactify on one side, it corresponds to having a super potential on another. Right, like
Right, no, but I'm confused about the story that the space is not changing, space on the.
yeah, the thing
Because
about
the mirror tool obviously does depend.
yeah, but think about toric varieties. I mean, like
Yeah.
a mirror to a toric variety, it's you start, it's the cool toric with some super potential that changes based on and pactification over the original toric variety. But the mirror to a toric variety, the space is the random.
And so, for example, this fourth column branches or biggest branch associated with this representation doesn't show up at all.
Okay, let me first answer your question one by one. So this space as a
Well, it does. Again, if you ignore this potential, you think very cheap on that. Looks like. Also,
Right.
for in the hypertoric case, there's some paper proving SYZ mirrors statements of this one. But hypertoric variety is SYZ very dual to this negative interval, this space with
right, it's the paper by Shu Cheng Lao and
So
no, I know for hypertoric variety, the space is like.
yeah, no, but I don't see how it covers analysis.
Okay.
Because here, the space is all done the same, so the same, for right, it means that you're taking some different space, and, I mean. Here, the story is that the space you have on the right hand side does not depend on the left hand side at all.
No, it does.
It depends on, you see those W, oh wait, the W, oh wait, no, they don't.
So it doesn't depend on what's called M.
So the right hand side, let me share what is depending and what is not depending on what. So the space is this guy. This representation has an interior, the interior edge, and an exterior. For the pure gauge Coulomb branch, we only take the interior part, right? That's for that is our space, and the superpotential depends on the superpotential depends on certain deformation parameter. That is, you have to make certain choice. The one that is canonically matched with the B side parameter choice is that the B side Taylor potential resolution is sort of like you're splitting certain clear parameters along a real line. And here, if we place these punctures, these things along a real line, then that will match perfectly well with the description on the B side.
I think Sasha's question was that the space YK, the space you're calling YK.
Yes.
That depends on that depends on the representation.
That's K and nothing else.
No,
That's right. It doesn't depend on this. It doesn't depend on the framing. Yeah, exactly. That's okay.
So this is why I don't see how this analysis works out.
But I don't see any contradiction.
Yeah, that's only go. Yeah, that's all.
Exactly.
okay, but wait, what is big N int?
And int means interior. So this is like an interior. Corresponds to interior edge. And this an exterior, the framing edge.
Framing stuff in the resolution. It is depending on the big N. I'm saying, the Coulomb branch is like we're going right for G and N. He's splitting off the B, but part of big N that is not a framing part.
Maybe, Sasha, you will be more happy with another version of the mirror symmetry, where on the A side, sorry, on the B side, I take the multiplicative Coulomb branch, which is the full G and the full N. And on the A side, I just take the sorry. I take the multiplicative version of that guy, and I drop all the superpotential. So let's say expectation is that coherent shift. This is like the open version. At both sides, I decompactify. Okay, so you had resolution. Here's the deformation.
But what happened to the N int? There's no more N int.
There's no more N int.
Okay, this I'm fine with.
Yeah.
But that's not what we're doing before, right?
Yeah, because what happens is that when you put on the superpotential on the whole space, it has a pole on the divisor that corresponds to an exterior. So that's why we need to delete that part. So this guy is this Gn, the full Gn, to remove some divisor.
But then I'm confused, but is the statement that it doesn't depend on M? When you devise the-
Yeah, after you remove the divisor, it no longer depends on the, yeah. I think that's thing
No, I mean,
Kamiser Webster. It's like, how to say? It's like just being very silly. Like you remove this guy, you become this, just the hypertoric case. So this guy's Coulomb branch is just say complex two-dimensional where you fibered over C and with one singular fiber like that. And when you remove this divisor, you're removing this part. So it becomes just a C star fibration over the base. So it's no longer sensible. It's no longer sensitive to what the singular fiber is at.
what is the definition of this interior?
This N interior is just the corresponds to the edge between the nodes. And the N exterior.
Like we don't work with arrows.
Yeah, these are interior, those are exterior.
How?
The framing.
Okay, I understand. I see what you're saying. I mean, I don't understand why it should be like that.
I don't understand either. Sorry. The only way I could understand is this is like very pleasant. It's more symmetrical. And there's a way sort of using K-theoretic cylindrical KRW algebra to prove it, but we haven't done that. So it's harder. I mean, and it's also very interesting because both space carries like a cluster algebra structure, and maybe it leads to other part of math as well.
Maybe the last question we could ask about this is there a way to formally relate this to students? Like this bottom,
This and that?
Yes, this bottom line, I cannot understand. The top line, I don't understand. So can you deduce the top line from the bottom line? Which is very simple.
I mean, they're related, but I don't know if you can deduce one from the other.
You can.
And they're related. There are like some, like Ben said, you can compactify this guy to get additive one. It's sort of an illegal operation. It's like a compactify some group to get the algebra. But one can do that, and then supposedly.
Do you believe the statement that actifying one side of Emerson should be kind of a superpotential on the other side?
Kind of, except that I don't even know how it works, but except the levels of the.
Yeah, but like maybe if you believe that, then you ask that. I mean, this is how they do in the paper by whatever it is for.
But also, it's compactifying on some computer extent because it's not compactifying in the sense of as simplex. Right.
No, it's not. Yeah, that
forms.
exactly. The holomorphic symbolic form is very different. So that's like a very illegal in some sense.
Talking about that, but you're right. You're saying the very few something.
Okay, that's true, but.
Or, I mean, this is how it works, like, if you look at the top, like, what you wrote on the top two lines on that board, like, C star and C have very different symplectic. The symplectic form on C star has a pole on C. But nevertheless, like, there's this heuristic, when you compactify C star to C, you add this superpotential term. And that superpotential term is precisely the count of, like, the new holomorphic disks that go through this divisor that you have. And so this the superpotential should be interpreted as a count of polymorphic disks through this new divisor that you are adding to space. That's the precise statement.
But is this kind of a practical position of this, like can you turn it into like algorithm so good? Like I tell you how to conduct the block and say.
Well, you have to be able to depends how good it can be polymorphic disks. I mean, can you do
No,
that?
I mean that's kind of the question. Can you say it without mentioning polymorphic?
Yes.
Like can you like do too large break?
No, there's but
Well, there's maybe one hope is like it's like this this multiplicative Coulomb branch can be obtained this by sort of a localization, like you kill something supported on the divisor. And this K-theoretic cylindrical KLW algebra can also be related to the usual cylindrical KLW algebra by some matching and some inverting some variables. And the hope is that if you can prove all the three players can be related to this nicer guy, you can start from this guy and do localization to get this kind of result. And there's on the A side, there's also a stuff removal function that goes from this things with W to things without W.
I think the question was about
Yeah, I know, but that's harder.
because you have to all
no, it's just the.
You mean like
There's some way you somehow not there's just some like what works over any field field spread and then the state which no this is nothing a little I just a little marketing now and then there will be some non-trivial state that in fact that's
well he told you what the super potential is, so he gave you some
how do they know that this is the right answer? Before I mean how check can I put it in like much bigger general?
Okay, if you want, you can work with FQ coefficient on the A side and try to do.
My question is, I mean, he gave the answer for some particular spaces, but how general is it? I mean,
the question is how to discover what the correct super potential is.
yes, I mean you're saying that somehow adding some particular some divisor amounts to writing some super potential on the right hand side. So is this possible to like promise and feel a break out of third or please break.
Well, I mean, there's a combinatorial answer to what the thing is, but like that you have to discover it by.
Like, is it just about what's is it defined rules? Like a specification defined rules, we don't see the function rules.
You mean Q is a rational number? Yeah.
So that means it does nothing to do.
The mathematical truth has different origins.
Yeah, usually the super potential has a like, parameter, the concept parameter. That's like the source of it, not the fact. You can in some ways it would set up. Like there's no like if you were trying to fully compact the body, just to say you're trying to fully compact the body into a proper manifold, there would be no hope because like I would be splattered.
No, I'm asking, is there some reasonable generality? It's not this procedure can be described.
Well, so far we only know about this kind of a quiver gauge theory. That's and that's and I don't know. I don't know a better motivation.
Or steeper program and they go through that kind of thing. But there are algebraic ways to find all of this. There's scattering diagram on the steeper.
Yeah, but here down in symptomatic, like holomorphic symptomatic, this might be forced under some issues.
Yeah, I mean, this might make.
But the compactification is not.
Yeah, that's the thing that confuses me. But once you compactify something, then you're using the super potential on the other side, replacing the brakes and the extra symmetry impact.
There's also maybe I want to pose a question here. Many of you guys are experts on cluster varieties, and there's some A cluster and X cluster variety. How's the homological mirror symmetry talk to these two sides? And should one view? So I'm working on finishing up a long overdue paper. So is there a way of using the symplectic two form, holomorphic symplectic two form in some sense to define the Weinstein structure rather than just put some random Kähler structure on the Fi Weinstein? space. Because that would be making it more canonical in some sense. They're using something like really there, holomorphic simplex form.
Are you not using the real part of that holomorphic simplex form to simplex expected?
One can use the imaginary part of that. Yeah, that is like one canonical choice. But if one ignore that, if one ignore the simplex 2 form, just build from scratch, is also one possibility. I'm like, I don't know, like currently, I don't know what's the right way to do. And it seems the first way is like is a better way because it really uses the duality of the torus. I am suspecting something similar could happen on this guy. I don't know. I have no idea. For the current approach, we just totally ignored the symplectic 2 form, holomorphic symplectic 2 form on the A side. Also, I should mention that Xinjin is using the real imaginary part of the holomorphic symplectic 2 form to do the Fukaya category. And her version is additive, I guess, on both sides. Yeah.
I think we're about to get kicked out of this room.
All right.
So maybe we should thank our speaker now.
Thanks again for the invitation.